So our work for today, our work for this week is on momentum and on impulse. And one thing, I'm going to go ahead and share my screen with you. One thing that happens is that I'm putting in each week, I put in a written summary of what we've done. And so if you go to Schoology, and if you go to your quarter two, week two, momentum, impulse, and Newton's laws, and if you go in your videos and summaries, you have one that says Phys, momentum, and impulse summary. So I already opened that here. And when you open it up, it just has kind of typed out what we're talking about. And so sometimes if you've watched the video already and you just need a quick look at something, this might be an easier way to take a look at it. Sometimes looking at this before the videos can be helpful, and sometimes this is more helpful than the videos, depending on how you learn and depending on what works for you. And so I'm going to use this a little bit, A, to kind of show you what it is, and then B, to talk through some of the pieces that we're doing this week. So the first thing we want to keep in mind is the idea of Newton's laws of motion. And Isaac Newton had 3 laws of motion, and these were based on observation and what he saw. Because if I were to take and set down, just like set down a pen or something and it started floating, you'd be like, no, that is not right. Because we know that that would not be right. And so there's things that we know, but he took and he did some research on exactly what's happening with those things and how it works. So these 3 laws of motion are this. First of all, the law of inertia. And the law of inertia says that objects at motion stay in motion, objects at rest stay in rest, unless acted upon by an outside force. Essentially, an object wants to keep doing what it's already doing. So if it is sitting there, it's not magically just going to start levitating or magically going to start moving around. There has to be a force present in order for that to happen. If it's moving forward, it wants to keep moving forward as long as there's no other force acting on it. So in space, if I take and I throw a baseball in space and there aren't any other forces around that are going to be able to impact that ball is going to go on forever and ever and ever. Now, if we have something rolling, there is friction on the ground, so that is an outside force, and it would eventually stop it. You see that in a reduced form if you're sliding a hockey puck across the ice. You don't have as much friction and it can slide much farther. Or if you play air hockey and there's that layer of air between the air hockey puck and the table, even less friction. And so that would go on forever and ever and ever, assuming no friction. So law of inertia, objects in motion stay in motion. Objects at rest stay at rest unless acted upon by an outside force. And what we're talking about today with momentum and impulse is mostly focusing on the idea of the first law. The second law we have used quite a bit because we've done these calculations, but it's F equals ma. The net force on an object is equal to the mass times the acceleration. And we spent quite a bit of time working on F equals ma a couple of weeks ago. And the third law is action-reaction. For every action, there's an equal and opposite reaction. So if I punch a table, the force with which I hit the table, that table is going to hit back just as hard. So if anyone ever accidentally get upset and punch a wall, there's kind of 2 situations. You either punch the wall and you go through it, or you punch the wall and break your hand if you hit a stud or something. Either way, action-reaction. So those are the 3 laws, and we'll do some more work with those in a couple of weeks. First law about inertia and an object wanting to stay in motion is what we're focusing on when we talk about momentum. So we have the 3 laws that are here. Now, I want to kind of go over here for a minute. Okay, inertia. If it has mass, it has inertia. We'll say more mass equals more inertia. And so for inertia, it's just an object's tendency to keep doing what it is already doing. So if it's sitting there and not moving at all, it still has inertia. It just doesn't want to move. It doesn't want to change what's already happening. Think about that. You get up in the morning, nice and comfy and asleep. You definitely have a lot of inertia. You don't want to move. Maybe you do. Maybe you're an early riser and an up and get 'em. I struggle with that. So more mass, everything with mass has some amount of inertia. And the more mass you have, the more inertia you have. Inertia is not dependent on motion. Momentum, however, is essentially a measurement. It's a calculation, a measurement of moving inertia. So we'll say that. Measurement of moving inertia. It has to be moving to have momentum. Inertia itself does not need to be moving. So I could have a giant rock in my yard. It is just sitting there. It has a lot of inertia. It has a lot of mass, so it would have a lot of inertia. But it would have zero momentum because it's not moving. On the flip side, I could take a little rock and I could throw it. It's not going to have much mass, so it won't have as much inertia, but it would have more momentum because it's moving. So inertia, anything with mass has inertia, but momentum, that mass has to be moving in order to have momentum. So how does this look? Well, we have an equation to do this. Inertia is just like, hey, whichever has more mass has more inertia. There's a direct relationship there. Inertia doesn't have a unit. It's just a concept. It's saying like, okay, more mass, more inertia. It's not going to change what it's doing very easily. Momentum, however, is a combination of how big it is and how fast it's moving. Think about it. If you have something that is, let's say, let's say a semi-truck started slowly rolling. You're not going to stop that really easily. Even though it's going slow, it has a ton of mass. So to actually stop it is going to take a lot of force because even though it's moving slow, a whole lot of mass would give it a whole lot of momentum. On the flip side, if you have something that's teeny, teeny, tiny and going really, really fast, you're not going to stop that very easily either. So it's that combination between the mass and the velocity that gives us our momentum. In fact, this is what it looks like. We have momentum is equal to mass times velocity. Now, here's the deal. Mass, we know, is m. Velocity, we know, is v. We can't just use m for momentum because we have it for mass. So somewhere in the Latin, Greek, I'm not sure at what point, the word for momentum started with a P. There's no P in here anymore, but our variable stays as a P. I know that makes no sense. I know it's super goofy. It's something you just have to commit to your mind. It's not even like pneumonia where it's a silent P, but it's there. There's just not a P. It's an invisible P. Here we have P equals mv. Momentum is represented by a P. Mass, velocity. Momentum has the units of kilograms times meters per second. And it's not like with newtons, we said, oh, kilograms times meters per second squared equals a newton. This isn't like that. With this, we're saying kilograms times meters per second, and we just leave it as that. Mass is measured in kilograms. Velocity is measured in meters per second. If you're given a mass in grams, you will need to get it into kilograms to make that calculation. So units for momentum look like this. Mass and mass looks like this. Velocity looks like this. These haven't changed, but that one is a new one. So we have inertia. Inertia, everything with mass has inertia. Momentum, anything that has mass and is moving has momentum. If either one of those goes up, momentum goes up. So the bigger the mass, more momentum. Faster it is, more momentum. Both of those pieces play into it. So if you want to screenshot that, you can. I'll erase that in just a moment. Any questions on this so far? All right, so we have this. We're going to take this. I'm going to erase it. All right, so how would this look? So let's say I brought some cars down here. We have lots of cars at my house. We got an ambulance. Ambulance is kind of big. And let's do a little race car here. Ambulance and a race car. Now, inertia if we talk about just inertia, ambulance has more mass, so it would have more inertia. So if it's just sitting there talking about inertia, or if they're going the exact same speed, ambulance has more mass, so it would have more inertia. It just has more stuff that you would have to get moving or changing in order to change what you're doing. If they're moving, let's say the ambulance is moving at, say the ambulance happens to be moving slow, and the race car were to be moving fast. Well, you could actually have the same amount of momentum here. Because if this mass is big, but the velocity is slow, and if this velocity is fast, but the mass is smaller, they could equal out to be what they are, or to be the same. So depending on what you have will depend on kind of that combination of what you'll have here. Now, that's what we're talking about when we're just talking about momentum. Just how fast it's going and how big it is. Essentially, forces get an object moving. Forces make something accelerate to have it start moving. Momentum, once your forces are done, momentum keeps it in motion. Let me talk about this. So there was one time, long time ago, that I was playing in a softball league. And softball, we were out there, we were out playing, and you could see a storm rolling in. Well, it was the last game of the season. It was playoffs, and we ended up winning. So we won the league championship. Wahoo, yay us! So we went out to Red Robin afterward. If you've ever been to Red Robin, you get free bottomless fries, and if you get a root beer float, that's bottomless as well. So we were at Red Robin and hanging out and having our burgers and our fries and root beer floats and whatever. And so then as we went to leave, that storm had rolled in. And so as I had gotten out of my car, it was dry out, and I parked my car and I got out and I was walking across the like grass pebble area, where they have like rocks and trees and stuff. Walked across that, rest of the parking lot, went into the restaurant. We had our burgers and our bottomless fries and our bottomless root beer. And we went back out, and it was pouring down rain, like pouring down rain. So we're all kind of standing there. We're like, all right, good job. High fives, good job. We won the championship. Yay, us. And I look at my car, and I'm like, got to get out there. And I didn't really want to get very wet. And so I was like, well, I'll just run fast. So I look and I take off. I'm running. And I go to walk through that or run through that kind of grassy pebble area. And as I do that, I like get a little bit of water on my foot, and I'm like, oh no. And my next step, apparently it's like a drain system, and it went down really far. So I stepped into about this much water. Objects at rest stay at rest. Objects in motion stay in motion unless acted upon by an outside force. So this much water created a really fast outside force on the bottom of my leg. It did not create an outside force on the top of my body. That kept on going straight into the water, completely soaked every ounce of me. It was ridiculous. It was real funny. And so I look up, I finally realize what happened. And I look up, I look around, and I'm like, nobody even saw it. Like, if that's going to happen, someone at least has to get a good kick out of it. And I look over, my friend's car is shaking. She's in there laughing so hard because somebody did see it. But that's what happens with Newton's law. If you ever trip or fall, it's Newton's law's fault. It is Isaac Newton's fault. You can say that. If you play a sport, you try and use Newton's laws against the other person and in your own benefit. So if you're playing basketball and you make a quick cut, you're hoping that the other person has enough momentum going that way so you can go that way and get around them. In fact, you try and set them up in order for that to happen. So we have this other thing that goes along with momentum, and it's called impulse, and it's how you end up stopping and the amount of force that happens on that. So let's go back to the big car. And no, we're just going to use this car. Just use the ambulance here. Now, let's say you have a car that's driving. And there is a stop sign up here. You can go back to that crazy friend driver. Okay, STOP, can't really see it. Okay, you have a stop sign there. And there's a couple of situations. Now the ambulance, now we don't need an ambulance here. We're going to use a regular car. Do a van. We have lots of cars here. Do a van. Now the van can drive up and make a nice slow stop and come to a stop. Cool. Or the van can be driving, and all of a sudden make a stop. Either way, you have a change in momentum. And so you have your change in momentum. We call that an impulse. So any change in momentum is your impulse. You're going from fast to slow, or you're going from slow to fast. Either way, that is your impulse. Doesn't matter how quickly or slowly you do that, that is your impulse. However, how quickly or slowly you do that will change how much force is required. So if you're driving, and you make a really fast stop, you have a short time, so you have a big force to do that. You slam on the brakes. Or if you're driving, and you see, oh, there's a stop sign over there. And you take your foot off the gas, put it on the brake, and come to a slow stop. It uses less force, but more time. The impulse, the change in momentum is the same. But the force needed to make that change in momentum is not the same. So we have this. We're going to say that our change in momentum, we say delta P, this is what represents impulse, is our change in momentum, is equal to the force times the time. So if you have a big force, you can change that momentum in a small time. If you have a little force, you can change that momentum. It just takes more time to do that. Another way that we'll write this is this, that MVF, minus MVI equals force times time. This gives us our change in momentum. We take our final velocity minus our initial velocity. Our change in momentum comes from us changing our velocity. So it might be because we're getting faster, it might be because we're getting slower, but either way, that's going to require a force for a given amount of time. Big force, small time. Big time, you can have a smaller force. So it can look like this. Sometimes people say, well, delta P equals, and we say big F times little t. If we have a big force, we have a small time. Or we can have delta P. They can be the same change in momentum. And we can have a little force times a big time. Either way, if the force goes up, time goes down. Force goes down, time goes up. Somewhere in the middle, they're both somewhere in the middle. Again, difference in your driving. If you have a big force, you slam on the brakes, you can do that in a small time. You drive a really fast car, with a real powerful engine, and you hit the gas, you have a big force on that car. It takes off in a short time. However, if you have a car that doesn't go that fast, you can get up to speed. I can get up to speed, but it'll take longer to do that. I was driving next to a little tiny, little Tesla the other day. I was just impressed. I was like, ooh, that is fast. Okay, Tesla had a huge force, a short time. Pew! We were in downtown St. Paul. It's not like they were going anywhere real far, real fast. But come on, if you're driving that, sure. My car, not a Tesla. I had force. It just took me longer to do that. So we have momentum on its own, and then we have impulse. Most of the time you'll have to figure out what's going on here to get your force and your time. And so I want to do an example of that problem, and then I want to take some time I want to do an example of this. I want to talk about your lab for this week, and then I want to set you up to do well on some of those practice problems that are a little bit more complicated. So I'm going to erase this. If you want to take a screenshot, do that, please. All right. And again, some of this stuff will show up if you go back into this. There's some examples here. There's the triangle method if you like that. It goes through the details of this a little bit more, and it goes with a couple of examples here. So I'll do some examples that are a little bit different from that. So you see it a couple of different times in a couple of different ways. So we're going to do kind of two parts to this. We're going to have a car. So say, I don't know, we'll say a 1,000 kilogram car speeds up to 25 meters per second. 1,000 kilogram car, regular car, speeds up to 25 meters per second. Regular speed, nothing fancy. We'll say from rest. So we have that set up. Now let's say they do it quickly. We'll say that the time equals, I don't know, 6 seconds. So we can say, and then we'll do it slowly. We'll say slowly. Say time equals 20 seconds. This is real slow. That's okay. So we have this set up. So we know that our mass equals 1,000 kilograms. We know our VI equals 0, VF equals 25 meters per second. And in this one, T equals 6 seconds. So we know that our change in momentum is equal to our force times our time. We want to know how much force is needed. Well, we'll say MVF minus MVI equals force times time. And if we're solving for force, we just need to divide by the time. So we have force equals MVF minus MVI over T. Well, MVF is 1,000 kilograms times 25 meters per second. MVI, it was starting at rest. So VI is 0. So 0 times anything is 0. So we have minus 0. Divided by our time here of 6 seconds. So if we take this and calculate it, we say 1,000 times 25 gives us 25,000. Divided by 6 gives us 4,166.7 newtons. So in order for that car to speed up over 6 seconds from 0 to 25 meters per second, it takes this force here, 4,166.7 newtons. Now, same car getting up to speed over 20 seconds. So we have same variables, except this time equals 20 seconds. So we can say MVF minus MVI, same rearrangement, divided by T, gives us our force. So we'll say 1,000 kilograms times 25 meters per second minus 0, same setup to start. This time we're doing that over 20 seconds. So we can take 25,000 divided by 20 seconds and we get 1,250 newtons. So considerably less force when the time goes down. Short time, larger force. 6 seconds, we have 4,166.7 newtons. Same change in momentum, this time over 20 seconds, and we have 1,250 newtons. So as the time goes up, the force goes down. I'll leave this on here. Any questions on this one?